Okay, to get warmed up with the question, what can Songbird teach us about language processing? Let's consider maybe this question you're more familiar with, namely, let's see now. The recent breakthrough in machine learning, deep learning has been fueled by applied neuroscience, right? That's a bit my claim. So what are the insights from neuroscience from the last, I would say, 50 years that have really made possible this kind of little revolution we had 15 years ago? Probably you would not all agree with me, but I hope some of you would. I think it's two things. So really what we learned from nature is that the type of nonlinearity of neurons, and that neurons, they pool their inputs in a linear and seemingly convolutive way. So this kind of insight has been instrumental, but you already got that insight about 40, 50 years ago. So what was the key, like 15 years ago, that triggered the revolution? And I would say it's the hierarchy of the visual system, right? We have realized that the visual world is represented on our retina, and then back in LGN it's again represented in the primary visual cortex, it's represented in secondary visual cortex, V2, V4, etc. So we have many representations of the world that are arranged in a seemingly feed-forward manner. And so that was essentially what triggered the revolution, to the realization that deep networks can be very powerful. And I would say this really comes from neurobiology and not from computer science, because computer scientists have actually, I would say, been hindering this development, because they had a famous result saying that a two-layer neural network is a universal approximator, which means any function can be realized by a two-layer neural network. But it turns out that in 2 layers, they don't generalize well. That's why people were not interested to use neural networks for the past 20 years, until they realized suddenly everything starts to work when you have deep networks. And so, yeah, with this kind of insight, I hope I have you on board with the idea that we can look at biology and we can take ideas and we can take them to computer science. And in this particular case, what my talk is about is language processing. So let's start with the main question that started everything. Before now I go there, I'm going to tell you about a revelation I had myself. This is like my personal view about behavioral science, because there is not just neuroscience and computer science, there's behavioral science. And I'm hopefully going to be able to convince you today that behavioral science reveals the algorithms an animal uses to solve a given problem, whereas neuroscience reveals the implementation. Right? So what I'm saying is, if you think about the computational problem, for example, like matching a template or searching or something like that, then animals, by their strategies, how they behave, can teach us the algorithm. And once you have the algorithm finally understood by doing many behavioral experiments, you can actually already get an idea of what the neural representation should be like. So neuroscience becomes almost like the control experiment. Right? In other words, neuroscience does not provide you with the algorithms, behavior does. Okay? And I hope this will become even more convincing after my talk. So the question is how do we compute vocal performance error, right? So what is that? We all know that when an infant grows up, right, it does babbling, it says baba, and we don't know what the infant is trying to say, right? It could be that maybe the infant is trying to say water, right? So maybe these two syllables, wa and ter, are mentally compared in the mind of the infant, right? Wa with ba and ter with the other ba. And maybe that's how they learn, right? But we don't know the answer. And the problem is, even if the infant had introspection, even if the infant were to understand what it does, it doesn't have language to tell us. So how can we ever find out, right? And we can do experiments with children and with pregnant women, and these are two research topics that are very difficult to approach. That's why I would say we may never find out what's the answer to this question, but I would like to convince you today that we can answer this question in songbirds. So what do songbirds do that is comparable to this particular behavior here? So the most studied songbird is the Zebrafinch. It's an Australian songbird. I'm going to try to play you one song so you get this out of the way. So you can see the the song consists of some introductory notes and then a repeated motif. And when a bird is very young, like 40 days old, if I plot the spectrogram, so the time frequency representation, then we see that they're very unstructured sounds and it's not clear what the bird is trying to sing. But as it gets older, 60 days, 80 days, and 100 days old, when it turns adult, then you can see that the syllables it produces are actually very similar to the syllables of the tutor. Here on top, the top spectrogram is the tutor, and you can see there's a nice match between these syllable pairs, between these, etc. And now the question that I just asked about infants would translate into when the young bird, 60 days old, is singing this particular syllable, what is it trying to sing, right? How does it compare the error generated by singing this particular syllable with respect to this template, which is the song of the father, typically. So that's essentially the question translated into the world of songbirds. And birds produce not just a song. You can see here is when the bird sings, they're from introductory notes here. And then these things are called syllables. They're like words, and there's a motif. The motif is being repeated, as I've shown. And birds also produce these calls, right? Short call, long call. So they have a rich repertoire of vocalizations they produce. And so my talk is about the strategies birds use to learn this vocal repertoire. So zebrafinches, they learn the song in two phases, right? There's a first phase, a sensory phase, when the bird listens to the tutor, right? That's like your 1-year-old listening to or like your 6 months old listening to the parents. And then it's a sensory motor phase that starts about after 1 month, where the birds start to sing themselves. And when they're 90 days old, they have produced a good copy. And these 90 days are usually compared to the first year of life in an infant, right? We know that an infant produces the first words after roughly 1 year. And that's this nicest analogy between zebrafinch song learning and infant speech learning. Now we know that when birds learn their song, they use a template matching algorithm, because they first are exposed to this tutor song. And you can actually remove the tutor from the first day on the bird starts singing, and they would still learn a good copy, which means that while the birds sing, while they practice on a daily basis, they don't really need to hear the tutor anymore. It's enough that they just have access to the memory of the song. Okay, this proves, like, you know, for a computer scientist, there's a memory and it's being accessed somehow, and then it's being used during this trial and error practice phase. And to really, if you have time, let's see, I can play you now also a song of a bird that is very young, 45 days old.
Hi, Richard. I know it works before, but at the moment we can't hear the songbirds playback.
Oh, you can't hear it. Oh, I'm sorry. Maybe I'll try at the end again, because I would not know what I would have to change here on my end to make it work. Very sorry about that. Okay, so here's a clever experiment that was just meant to address this question. What is the performance error in birds? And the experiment goes like this. You play a song just of 3 syllables, A, and then the bird sings A, and when it does that, it's still young. You play another song, A, B, and B, A, B, and what the bird will do, it will sing A, B, and B, A, B, A, B. And the question is, how does the bird go from A to A, B? And you might say, well, that's a trivial question. You just add the B and that's it. But then when you look at the data very carefully, what you see is that the bird sings first A, and then it just sings A, and places the B at the end, and only then it starts producing A, B. So it seems that the bird needs to first learn the transition from A to B, and then it needs to learn the transition from B to A until it can really sing the song. So maybe to learn transitions is not such a simple thing for birds. So new syllables tend to appear at the end or the beginning of a song. Okay, now if you play A, B, C, and when the bird is still young, sings A, B, C, they're shown over here, the syllable A, B, C, you can see. And then you start playing A, C, B, which means you just reverse the 2 last syllables. And then you ask yourself, well, how is the bird going from this song A, B, C to A, C, B? Then you see that the bird, after you switched from the source to the target song, they will sing ABC for some time, like 8 days or so, and then they will sing neither song, and after about 15 days, they will start to sing ACB, which means it takes them quite some time, but if you want to look at really the microstructure of what happened, then you see, well, the birds needed to learn first the transition, AC, that's the green line, then they needed to learn the next transition, CB, and only when they had all three transitions, also BA, they were ready to sing this new song. Again, suggesting that to learn a new transition from a known repertoire is actually difficult. Now you might say, well, in humans, but we are pretty good at making new transitions of sounds. And then you have to go back and ask yourself, really, is this really the case? So these authors who made this discovery, they also studied actually infants. They looked at what happens when infants 6 months old roughly produce new syllables. So this study now in humans was done after the study in songbirds, and I'm going to claim actually really we learned actually that infants do something very similar to songbirds, and thanks to the hypothesis which we gained from songbirds, we could actually start addressing it in humans. Okay, here's the frequency of reduplicated transitions during babbling, right? This is an infant saying da, 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 just repeating what it, one syllable. And when you look now at the time before 50% speech, right? 50% speech is the time when when about 50% of what the infant produces in terms of sounds can be understood by an adult, has a meaning, and the rest is just babbling, has no meaning, right? When you go back from this time, then you could see the amount of duplication does not really increase. So it's not really true that the infants first have a phase of reduplicated babbling, reduplicated babbling, and then variegated babbling. There seems to be something else going on. But then now let's go back to our hypothesis that learning new transitions is hard, right? And then you can see, oh, actually, when you align now from syllable first appearance, right? So 0 is the time when the bird produced, when the infant produced a particular syllable, let's say da, for the very first time. And then you can see then there would be a lot of reduplication, but as the time goes by, the amount of reduplication goes down, right? Suggesting that it stays constant here because the infant makes up new syllables maybe 1 a week or so. They don't appear all at the same time. And when an infant produces a new syllable, it first needs to repeat it and then slowly learn to make transitions with other syllables. And indeed, when you look now at variegated babbling like da, ga, then you can see that as time goes on, the amount of variegation increases. Now this is again a probability axis here, and it's just logarithmic, that's why it's negative. But the curve goes up, means the probability of variegated babbling for a given syllable is actually increasing in time. So this, I find, is a beautiful analogy between behavioral science providing us with a hypothesis and then making a fundamental discovery about language development. Okay, now let's go on. Now we go towards computer science, right? So when you give infants actually a song birds. When you give birds a song A, B, I, B, and while they're still young, you can give them a new song A, B prime, where B and B prime are just apart by 1 semitone, right? So da, 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 and then da, 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 da. So it's a small deviation. What will birds do? Well, they will sing the old song for some time, the old B, and then after some time, they will bring the pitch down to the new syllable, right? Suggesting that birds can not only change errors in the syntax, in the order of syllables, but also in the spectral content or the pitch of the syllable. So birds can correct pitch spectral errors. Now here comes the interesting part. How do birds deal with combined structural and temporal errors, right? So we know that birds can produce spectral mismatch, they can produce temporal mismatch. And now when you have both spectral and temporal mismatch combined, right? It's like, you know, you having a piece of text that you need to write, and then you realize, oh, actually I should put this sentence first, and then I should actually change this word by that. So what do you do first? Rearrange the sentences and then replace the words, or do you first replace the words and then change the sentences? I would say everybody has their own personal strategy of changing a sequence, but there's no universal strategy because this is known as a quadratic assignment problem, and it is NP-hard, right? NP-hard means we don't know an efficient algorithm for treating this problem of how to optimally correct sequence and spectral errors in a sequence when it's very long, right? And if you have already a sequence of 20 elements, to try all the factorial permutations for 20 is kind of not within reach, even within the best supercomputers. So we don't know how to solve this optimally. It's an NP-hard problem, right? And so I think it's particularly fun to realize that we can give an NP-hard problem to a bird and see how does a bird deal with an NP-hard problem. For then, of course, N is not very hard. It's not a big number, but maybe it can be 8 or so. So a bird can learn 8 or more syllables. So it's not a trivial problem. So obviously the birds will not solve it in an optimal way, but the question is, what kind of workaround solution will they choose? How do they take a shortcut in this complex problem? So here's I'm not going to give you all the insights, but here's we have done hundreds of experiments to probe this. Here's just one that is particularly interesting. If you give a bird first a song A, B, C, and then you give it a new song A, B minus, C, B plus, right? Then you would say, well, if the bird is smart, it would take the B and transform it into a B minus, because then it already has A, B minus, C, right? And just needs to learn that additional syllable. But that's not what birds, all of them do. Here's one example of a bird that sings A, B, C, and I show here the songs just as a stack plot. These are hundreds of songs produced in 20 days. And by color, I show the pitch. So you can see the pitch goes from blue to red, which means from low to high, which means this bird increases pitch. It's going to sing A, B plus C, right? So it takes this new syllable here, B plus, but sings it at the wrong place, which means this poor bird will have to correct not only for the pitch in B, it would have to rearrange the song as we just learned before, right? So the bird really created a big problem for itself. And he's not the only one. So here are 4 birds. You can see this one decreased pitch to B minus. This one first went up and then corrected, realized, oh, actually it's smarter to do this, but these 2 didn't. They went to the wrong syllable. That's one of them. So I would say, I think if I remember correctly, half the birds went up and half the birds went down, suggesting that when they see an error in their sequence or in their that they will not really they will not really care about the context in which the error occurred, but they will just correct the error regardless of the context. They have like a, we'll call it context-free error correction mechanism. And, but it's actually not random really, as it's shown here in this experiment. If you do another experiment, so I would say, okay, they do syntax blind vocabulary learning. That's how you can call it, or context-free, you can call it. I'm not sure I'm allowed to say context-free in the face of Chomsky and what it means in linguistics, but I think it's describes pretty well what's going on. If you do another experiment, actually that reveals it's not really random, it's actually greedy. So here's another very interesting experiment. You first teach a bird A, B, C, B plus, right, with 1 semitone between B and B plus, and then you teach it the song A, B plus, C, B minus. So you're asking the bird to make 2 changes, right? Now, when you look very carefully, you could see for this particular B, there's 2 possible ways of correcting the error. The bird could either go and make a B2 plus, that's a far distance, right? It's 2 semitones away, or it could correct to B minus, that's a short distance, 1 semitone away, right? So you're offering the bird 2 solutions. You're offering the bird to go a far distance, 2, also plus 2, you would say here, you will see there's the symmetry case here, there's also 2 semitones here and only 1 here. So you're offering the bird a solution of 2 plus 2 semitones, but he gets everything right. Or you offer the bird a solution 1 plus 1 semitone, but it gets all the sequence wrong, right? So what will the birds do? And here they don't do half-half. Here it's very clear, the birds, they all do the wrong thing. So they will go close to target. They will just take the greedy solution. They go from the source to the closer one. You see the distance here in pitch on the y-axis is actually small. So the birds, every of these lines is 1 bird, and every point is 1 day. You can see the birds, they just go towards this target here. They take the greedy way, but that gets them the syntax wrong. So you could, summarize these findings that optimal sequence learning is NP hard. And the computation of vocal performance error in birds is modular, right? They have kind of a pitch module. They correct the pitch and they do that independently of syntax, because we already know they cannot do both at the same time. It's NP hard. And then the pitch module is actually greedy. Okay. Now, for those of you who are computer scientists, maybe you already can think of what is actually the exact algorithm in computer science that has these properties, that is also greedy, and that has the way of being kind of subject to the constraint that the bird learns all syllables. It's like a constraint optimization problem. It's actually a linear assignment problem, not bird-solve. So the bird-solve, the linear assignment problem that we all know because we take taxis, right? A taxi company has a certain number of customers in the city, and the customer is like the target and the taxi is like the syllable. And when they get calls, they need to assign taxis to customers. And they don't care which taxi goes to which one. All this they care about is to minimize some kind of cost. So the taxi is like the syllable, the customer is the target, and what the companies they minimize is the average pickup time, right? They want to, or maybe the fuel if they are environmentally conscious. So they want to get the taxis to the customer as quickly as possible. And the total pickup time is the overall pitch change. That's what birds do. They just solve this exact same linear assignment problem, which in computer science has the same complexity as matrix inversion. So it's not a trivial problem. It's a cubic problem in complexity in M. So, and I would say that is a good approximation of what birds do. And when we saw this, we thought, oh, let's now find out how do people in NLP, how do they compare texts? And I asked my PhD student, Nikolov, to look at papers, and he found this paper. He found the paper about word movers distance. I'm not sure you've heard this, but it turns out this is exactly what birds do. So, and this paper was published in 2015, and our paper was published in 2017. So the computer scientists were faster. They got it right before us. But let me explain how it works. So if you have a sentence here, the president greets the press in Chicago, and another one, Obama speaks to the media in Illinois, then you can compare the words, you can align them like this. Obama and president is similar, speaks and greets is similar, media and press, Illinois and Chicago. So then you can add up all these individual distances and you arrive at word movers distance. So it's a transport problem, right? You transport every word in the source to every word in the target, and you sum up the distances. And the word distances they choose here is just the famous word-to-vec, or you can take some other word embedding that is amenable to being used. And then it turns out in 2015, this was the best algorithm that was there, that was shown in red. This is the error, so it has the lowest error. It produces the best document retrieval performance. So I found this very cool that birds through evolution had found a solution to a problem millions of years before actually computational linguists discovered a very similar solution of how to compare sequences of symbols. And so we did more experiments. I'm almost done now. I see I'm sorry running out of time. This is almost the last slide. So we did another experiment that I find very interesting. When we taught the bird to sing AB, AB, and AB plus, and there's only one semitone away, then birds would do it. So these green dots are the lines are different birds, and this is every time is 1 day. So it takes them a few days to go to the target. If it took 2 semitones, well, the birds will still do it. But then when you do 4 semitones, right, when you make the difference between the source and the target 4 semitones, then none of the birds has done it. So what they did is they used the call to match the target. And so I found this very interesting. It seems that in this linear assignment problem, the cost is not really linear. They don't go at infinite distance to compute the error. If the error is too far, they will say, forget about it. I use some other strategy, like I use the call, or I invent a new syllable, or I just do something different. And then I thought, okay, cool. Now we have something where we are ahead of computer scientists. And then there was a paper in 2019. It's called Wasserstein-Fischer-Rao document distance, where they do essentially this. They say an unbalanced optimal transport theory. So what they changed is now, if you have one sentence, Earth is a blue planet, and then you have another sentence, most of our planet's surface is covered by water, but I wish it was beer, right? If you were to compute the similarity between these two sentences, then you could actually forget about, but I wish it was beer. So that's essentially what the Wasserstein-Fischer-Rao document distance does. It allows you to compare sequences of different lengths, and the things that are not really relevant, or the things that have a distance that is larger than some threshold, are just being discarded, right? So here beer, and it's not really related to this stuff, it's never blue, and it's not, so this part of the sentence can be neglected. And it turns out, well, this is even better than the word movers distance, right? Here, word movers distance, which is this linear, the solution to the linear assignment problem that birds perform. You can see that the precision achieved in a retrieval task by different variants of this WFR distance is actually is better. So again, birds seem to have known that when distances are too large, there's no point in going and using those things, and rather use another strategy. And it seems in NLP this also pays off. So I hope this was clear. This is more or less this is where we are today. Maybe I just give one slide about what could be the next thing, right? What could we learn next about how birds learn a song, and how could we potentially inform, you know, computer science and machine learning with insights for the first time to be ahead of the game, if that's possible. I would claim the trial by trial learning strategies that birds use are very interesting. So namely, right, we know that the theory of reinforcement learning, right, which originally was just an idea. It was an attempt to model this famous result of classical conditioning by Pavlov, right? It was an attempt to implement this behavioral insight into a computational theory. So it was derived from biology once more. But when you do reinforcement learning, you know that it's very complex, because once you have a large search space, it's infinite. So you need to explore, and you can't be greedy all the time. You need to keep exploring to some extent, right? So how do you explore? And what is the exploitation trade-off that you'll use? That's an interesting question. But even more interestingly phrased, it is, what is really the microstructure of directed exploration, right? How can you explore in a smart way, in a goal-directed way? What should be the goal of exploration? And computer scientists, they have now these concepts of curiosity and empowerment. And I think these are good ideas that are out there. And I think by looking at birds, what is the trial by trial learning strategy, we can actually inform, provide new ideas for how curiosity, what's the mathematical formulation of curiosity and empowerment for reinforcement learning. Okay, that was it. Thanks very much. Here we are a small research group, and we have nice funding from the Swiss National Science Foundation. I'd be very happy to take questions, and I hope it was more or less clear. And while you maybe ask questions, I will try to play the sounds one more time.